Well, I see a lot of familiar faces in here, but if you don't know me, I'm Liam Cassidy. I'm a PhD candidate at University of Melbourne. And here I work with Dr. Andrew King, who's in the room right now, Dr. Joe Brown, and Dr. Tilo Ziehn, who's in the Zoom here. So today I'm going to talk about some of the work I've been doing recently. A lot of the stuff I share is up for publication in Earth's Future, and we have got some strong feedback from the editor, some positive feedback. So we're hoping it'll go through kind of the final processes in the next few weeks. So that's promising. And I shared a QR code at the end of this with the preprint that's available. It changed a bit in the revisions, but this talk is mostly around the kind of the methods and what we're looking at right now. So my research, like the title said, and like Shane said, I'm concerned with kind of temperature extremes and general mean state regional climate change after net zero. My work is focused specifically on net zero CO2 right now, although next steps we might be looking at more complicated or more comprehensive models with other GHGs. But basically right now, current findings and publications around net zero CO2 lean on experiments that are kind of idealized ramp up of CO2, either emissions or concentration, depending on the study. And then they hit a point where CO2 is basically shut off, like CO2 emissions, to kind of simulate or represent a transition to net zero. It's obviously idealized because it's an instantaneous transition. But current findings show that on kind of multi-decadal, 100-year type timescales, global mean surface temperature changes, but the change is near zero, and models have kind of different values. But this quantity for these cases is known as ZEC. It's basically the global mean surface temperature change after emissions of CO2 are ceased. But our colleague Alex, I don't think he's in here, but he's also a UniMel PhD candidate, found that although the kind of global mean surface temperature changes after net zero are small, the changes are significant compared to the natural variability represented by the ESMs that participate in these studies. Some other more recent findings are that kind of regional temperature changes after net zero can be significant, but they're very different in space and across models. I think some of the figures I'll show will highlight that. Some of the work I did recently in my first manuscript is kind of representing point 4 here. We looked at temperature extremes in kind of a simpler way and found that after net zero, temperature extremes over land are expected to decrease generally, but the kind of decreased values are highly regional dependent, and the reductions in temperature extremes tend to favor the kind of large continental land masses in the global north as opposed to the tropics and southern hemisphere. And then another robust finding by a lot of these papers have this and other papers around stabilization, but in Matt's paper here on the bottom, after net zero, the Southern Ocean is projected to continue to warm, which is a very common finding in this kind of research area. So basically from those points that we kind of have so far, we're kind of developing a research focus for this kind of second paper that's going to come out hopefully soon. And we focus on temperature extreme scaling relative to global warming level during warming climates and net zero. So we kind of are comparing the scaling regionally for temperature extremes during a warming period like we're in right now versus kind of a simulated net zero climate period. And one thing that's been a little bit harder to study, just given kind of small data availability, is the mechanisms that might drive regional changes in temperature extremes, and how different models basically have different mechanisms to different degrees. So just a further study for those. And so the methods for the paper we're kind of working on now We're using the Zero Emissions Commitment Model Intercomparison Project, otherwise known as ZECMIP, because that's too much of a mouthful. And basically, the MIP is full of some idealized experiments to understand global and, well, it was global climate response to net zero CO2. And we use these to study kind of regional changes as well. The experiments are emissions driven, at least when in the net zero type mode. I'll comment on that in a second, but the emissions driven basically implies that instead of prescribed atmospheric CO2 concentrations like are in the SSPs and RCPs previously, the carbon cycle within each ESM determines the CO2 concentration. So it's a bit closer step to the ESM simulating how Earth system responds to emissions of CO2. And it is a multi-model ensemble. There are experiments within the MIP that are prioritized that have more models. For our research here, we're looking at 3 of the actual experiments in ZECMIP. So the way the experiment kind of works, there's an illustration here on the right. Starting from a pre-industrial condition, the models are forced with the 1% CO2 per year positive kind of emissions phase, which is denoted in the red. Different ESMs run this in emissions-driven mode and some run in concentration. I think it was up to the discretion of the modeling institution to figure out which they could couple with the net zero phase, which is represented by the flat lines, the green, the yellow, and the blue. So the 3 experiments we look at are called the 750, 1000 petagram, and 2000 petagram branching experiments. Essentially, the experiments for CO2 emission cessation once those cumulative emissions levels are reached. So for the 750 case, it would be the lowest branch, and then the 1000 is the middle branch, and the 2000 is the top. So those are basically ascending order of, you could call it CO2 emissions prior to net zero. For our work, we kind of wanted to look at climate changes during the net zero period relative to while the climate is warming. So we created these climate slices. Along the red curve, I'm going to refer to those as the warming climate slices at each of those cumulative emissions levels, the 750, 1000, and 2000. And then the net zero climate slices are during the, I guess, the more stable looking portions of the experiments here. And those are 30-year climate slices centered at 85 years after CO2 is shut off. So it's basically the end of century after net zero is reached. And I don't know if I mentioned, but the warming climate slices are 30 years as well. Previous work used 20, but we had the capacity to take some extra years on and maybe filter out a little bit more variability. And so some of the stuff we're seeing, I didn't include the global responses, but I can send those out shortly if you want. So this shows the regional, basically average temperature changes after net zero. So the anomalies for this and for some upcoming figures I will show are basically the seasonal temperature during net zero subtracted by the seasonal temperatures during the warming climate period. And so on the right, the columns represent each of the ESMs. We use 3 because these were the only 3 that performed all 3 of the branching experiments. And row-wise, those are the cumulative emissions levels. In the figures, there's also, I added some stippling and cross-hatching. So the stippled portions are where temperature decreases and precipitation increases. I didn't include the precip maps into this presentation because they're kind of hard to look at, and this represents them. In this, the cross-hatching is where temperature increases and precip decreases. So hotter, drier cross-hatching, and then stippling is kind of wetter and cooler conditions after net zero. And so what you kind of see here is that there is some very significant model diversity, just generally as a first glance. Like the Muroc model on the leftmost column has a lot more cooling over land at all three emissions levels, whereas the ACCESS, there's lots of cooling over land in the 750 and 1000 petagram case, but continued warming in the 2000. And the UK ESM has that feature as well. Each of them at each emissions level does show some Southern Ocean warming, which is kind of a pattern we expect to see. And there are some strong kind of localized cooling and warming patterns that correspond to precip increase and decrease, which is kind of an interesting finding that I'll talk to a little bit more here. So this is now, I took out the 750 petagram and 2000 petagram case just to focus on the 1000 here. And so I became kind of interested in this relationship between temperature and precip and how there are kind of pockets of significant cooling after net zero where precip increases. For example, during JJA in the Muroc model, you can see over kind of Western Europe and the Mediterranean, strong cooling with stippling, meaning increased precip here. And that's also for the UKSM. The cooling isn't as strong as the Muroc, but you can see it is localized. I mean, it's surrounded by areas with pretty negligible temperature change or even increases. Kind of conversely, for the ACCESS model, in the sort of red circles I put here, for JJA, there's these pockets of strong warming in the kind of central North America and Northern Asia. Those have the hatching, so those are areas where it's becoming warmer and drier. And similarly for DJF, all the models have a kind of a local cooling and increased precip over northern South America, kind of the Amazon region. And in DJF, there's over Australia, the Muroc and ACCESS do have kind of signs of increased precip and strong cooling. But there's also areas that the models don't agree. So for instance, in the DJF bottom row here over Southern Africa, the Muroc model kind of has this strong pocket of cooling with increased precip, whereas UK ESM and ACCESS have a bit of warming locally with a drying trend after net zero as well. So kind of looking at the temperature precip relationships from our study, started to form some questions around whether, because these are, seasonal mean state changes, and those can often relate to changes in extremes locally. So we wanted to look at changes in, circulation and precip, local hydrology, to see if that was a determining factor in the sign and magnitude of temperature changes after net zero. So for our work, we're looking at TXX scaling. So TXX is the kind of annual single day maximum temperature extreme. And so we're looking at how that scales relative to the global surface temperature anomaly, so kind of the global warming level, to look at whether those scaling values change during, like if they're the same kind of scaling during net zero as they are during a warming climate. The scaling is kind of a good way to look at regional climate changes. It's a covariate in a number of studies. And so for TXX, usually in most land regions, the scaling is greater than 1-to-1, meaning for a 1 degree change in global warming level, you would expect TXX, or your local temperature extreme, to change by more than 1 degree. So if it's 2-to-1, TXX might be 2 degrees C higher than pre-industrial, whereas your global warming level might be 1. It's due to the difference in land sea heating. That's okay. And so local differences, scaling is not the same everywhere. So showing by this plot on the right, is from Sonia Senavaratne's 2016 paper. And this shows TXX values at 2 degrees C. Oh, shoot, I forgot to include the color bar, sorry. But there are pockets where you can see the scaling is kind of higher, it's elevated. So over kind of the Amazon region, over the Mediterranean for this example, you have higher scaling compared to other land regions. And that's local scaling difference are often due to kind of local feedbacks like ice albedo or soil moisture. Our work kind of is shown on the left here. So this is the scaling values for the warming period. So this is the change in TXX over the change in global mean surface temperature during those kind of warming climate slices. And you see some definite variation between the models. But they do pick up on some of the hotspots that you see from the work on the right. Kind of pops out in Southern Africa for at least the Moroccan ACCESS, and then the Mediterranean and kind of North America as well. And the Amazon region also kind of pops out. So yeah, this is during the warming period. These are the scaling values. You can see they're kind of well above 1 in some areas and then kind of consistent in others. So this is now showing the change in scaling after net zero. So it's basically computing your change in TXX and GMST during that zero period and subtracting it by that plot we were just showing before. And so what we can see here is, again, there is definite model diversity with ACCESS and MIRAC kind of having a stronger hemispheric difference in these scaling reductions, where the Northern Hemisphere has kind of a significant decrease in the temperature extreme scaling compared to the tropics and the Southern Hemisphere. Whereas UK ESM is a little bit more consistent, near zero changes, but mostly a TXX scaling decrease after net zero. And so kind of with those changes in extremes being very heterogeneous in space, and the relationship between local summertime temperatures and precip in mind, those two kind of in mind, we wanted to look at possible drivers of why those TXX scaling changes occur to different magnitudes in different regions. And so as a starting point, we looked at local precipitation and westerly wind patterns. So the plot on the right, the left, this is for the, again, for the 1000 petagram case only, just to focus in a little bit more on one of the experiments. So on the left column, this is the anomaly during the warming climate period. So over the land surface, you can see the coastlines there. Over land, that's the precipitation changes. I think these are in percentages, my bad. I forgot to include the title there. And then over ocean, these are changes in the 850 HPA westerly winds. So during the warming period, the westerly wind anomaly is pretty consistent between the 3 ESMs. And it's indicative of a poleward shift of the westerly winds and possible storm-bearing systems. But interestingly, the precip, so I'm kind of focused on Southern Africa here, sorry. The precip locally during the warming period increases for ACCESS and UK ESM. However, the MIRAC has kind of a drying trend, especially in the southernmost part of Southern Africa there during the warming period. During the net zero period, it's not as clean. The westerlies do kind of show a general reversal with those reds those red hues that are kind of displaced poleward in the warming. They do have sort of a element of equatorward shift there. So kind of a step towards reversal, but not as clean, obviously, as the warming climate. As for the precip patterns, there is they step in the direction of reversal. So like with the ACCESS and UK ESM showing the kind of wetting trend during the warming climate, they show drying during the net zero. And similar with the MIROC, though a bit more subtle, the initial drying of the southern part of the region is shows like a wetting trend after net zero locally. So we kind of wanted to take this a step further and understanding that local soil moisture moderates and can amplify temperature extremes in mid-latitude regions, especially that's been studied here and over the Mediterranean region as well. So for this case, again, the warming climate anomalies are in the left column with the net zero in the right. ACCESS actually shows a drying kind of trend, a reduction in soil moisture during the warming period, which is interesting because it's kind of maybe opposite of what you might expect with the precip patterns actually increasing during the warming. And this drying trend for ACCESS specifically kind of continues into the net zero period. For UK ESM, the soil moisture anomalies sort of follow what intuition might say based on the precip study. So increased soil moisture during the warming period and then a decrease during the net zero period when UK ESM projects drying. And then so for MIROC, these are much stronger signals. So there's a really strong drying trend in the warming climate period followed by a bit of a rebound. So like increased soil moisture after net zero, which does kind of follow the precip patterns, but it's a very, very pronounced pattern for this. And so kind of tying this all together, we wanted to at least get a jumping off point for studying maybe close to storylines of local changes and extremes after net zero. Because the forcings are quite small, studying these specifically in like non-probabilistic ways, but looking at kind of physically explainable changes in net zero might be a valuable avenue for future research. So on the far right, so these two, the precip map and the soil moisture are what I showed just previously. And then on the right, these are the zoomed in changes of scaling, temperature extreme scaling over the region. So the left being the warming climate and the right being net zero. And so you can kind of see the MIROC really stands out as one that has a really strong TXX scaling in the warming period and a strong reduction, which looks very similar to the soil moisture change for this model. The other two, the signals aren't as strong, but I guess for the ACCESS model, there is kind of a hotspot in scaling over Southern Africa that does match up with the soil moisture change, and then a near zero change in scaling for the net zero period. And then UKSM is kind of somewhere in the middle there. But we did this for the Mediterranean as well, for kind of the JJA trends and TXX scaling. And we do find kind of a similar story that changes in wind patterns, precip, and potentially local kind of surface patterns could play a role in the TXX scaling there as well. So I guess in conclusion, we find that changes in temperature extreme scaling after net zero, they're generally favorable changes. There's decreases in scaling, regardless of where the global mean surface temperature goes. However, they're very regionally and model dependent and deserve a little bit more study in that way. And so generally, I guess we find that storylines type approaches can be useful compared to the kind of commonly used statistical methods in climate science when we have such a small number of models and members and things. So it could be promising, and we're going to be looking a little bit more into that in the future. Ongoing work. So right now, this was for these idealized ZEC net zero type runs. But now I'm kind of looking at changes in more plausible scenarios with overshoot and periods of net zero. And this, so it'd be one of the SSPs, like SSP 534. And since it's an SSP, there's a lot more model data, including some ESMs that have many members. ACCESS has like 40, and then some of the GIST models have a few. So looking at the uncertainties between single member multi-model groups and single model multi-member, and kind of looking at how those compare. It's going to be an interesting study, I think. And then, yeah, keep an eye out for a paper might release in Earth's Future in the next couple of weeks. I put a little QR code here for the preprint. There are some changes, definite changes, but the story stayed pretty similar after the revision. So yeah, keep an eye out, and thank you for your time.